Hi everyone, welcome back to this week's ZX seminar. So today we have Leah Ye, and she is currently a PhD student from University of Oxford, and she's going to tell us about how to understand stabilizer codes using the ZX calculus, which is unofficially Grok 4. And the floor is yours, Leah.
Okay, mic check. Okay, good. Hello, everyone. Welcome to another week of the ZX Calculus seminar. Thank you to the organizers for hosting physically and in person and online. Um, so this is our in ongoing work, but we're quite further along now on ZX Calculus normal forms for stabilizer codes, and specifically how to relate these to tableaus. So the roadmap of this talk is going to be three parts. First part is just going through a few different representations of quantum error correcting codes, more than a few. The second part is our main result, which is an AP normal form, but generalized from just stabilizer states to any Clifford isometries. So any isometries in the Clifford fragment or stabilizer fragment of the ZX calculus. And the third results, collection of results is a lot of things that we can do using this second part of the talk, this isometry AP normal form, to connect the different representations in the first part. So first, here's a smorgasbord. Well, before we get to the smorgasbord of different representations that are commonly used for stabilizer codes in quantum error correcting codes, we'll just go through some terminology. Sorry, this is a bit dictionary style. So any m qubit stabilizer state is uniquely determined by m independent Pauli operators that are stabilizing it, so Pauli strings. And instead of a stabilizer state, a stabilizer code is fixed by n minus k independent Pauli operators. And they just have to be independent, so this is a non-unique choice. You could take linear combinations of them, and that's still fine. And these are called the stabilizer generators of the code. While this fixes the code, this does not fix which logical states are mapped to which physical states. To do so, you need to additionally specify 2k more Pauli operators, where k is the number of logical qubits of the code per code block, and n is the number of physical qubits that those k logical qubits are encoded into. So these 2k more independent Pauli operators are called the logical operators. And again, you can also take linear combinations of those. The total number of Pauli operators that we've specified so far here, which is n minus k plus 2k, which is total n plus k, are independent Pauli operators. These together make a complete stabilizer tableau, fixing an encoder map E. So the crucial distinction is that a stabilizer tableau just fixes just the code, and it's just each row is a stabilizer generator. And the complete stabilizer tableau, in addition to fixing the code space of the code, also fixes the logical operators. So we'll get to a bit more about that in a bit, but this is just terminology. So it might be clearer in this slide. So this is what I think of or call as the encoder picture, because usually people describe codes using just the stabilizer generators, and this gets you quite far, including most of the relevant properties you're interested in of the code and how good it is for quantum error correction. But specifically, if you don't want just a quantum memory, but you want to actually do something useful with the code, then you need to specify or know what kind of logical operations are interesting that you could do with some kind of not too much error physical implementation. So I think of the encoder picture, and this is, I guess, a well-studied, or I guess growing an interest area of study with quantum error correction as well as with ZX calculus researchers, is to look at it via encoder maps. So this encoder map E for a code, you could have many choices, but for that code, describes how certain k logical qubits are encoded into n physical qubits. Take that encoder map, it's an isometry, which means if you compose it with its adjoint, then what you get is identity on the k logical qubits. So this E dagger is called the ideal decoder. So it's the decoder that annihilates anything that's outside your code space, and correctly decodes the things that are in your code space. So if you do these two E and E dagger in the opposite order, since you're going from N to K, which is usually less than N, and then back to N, like you're compressing some information, so it's not the identity. It's actually the projector onto the code space. So throughout this talk, I'll use the symbol pi to refer to this projector. And one way you could decompose the projector, or many different ways, I guess, is to just pick N minus K total independent stabilizer generators. And the projectors for each of them compose together, since they all commute, the order doesn't matter. Because that succession of projectors, one for each stabilizer generator, makes the code space projector. The code space is also the image of the encoder map E. So one way to think about that is if you do the encoder map, this isometry E, and then you do the code space projector, that's the same thing as if you just did the isometry E. And this line here shows that if you do encoder, then encoder dagger, then encoder, which is the same thing as encoder, then projector onto the code space, that's the same thing as just the encoder. So not only the projector preserves the image of E, but also any poly operator S, whether it's measuring or doing those polys as gates, that also preserves the code space of E and stabilizes it. So we're familiar with single qubit poly gates, but just as a refresher, it is quite convenient to draw and like contract circuits for doing multi-qubit poly measurements in the ZX calculus. So here is a typical measurement circuit. I've only drawn two C-naughts, but you could do a dot, dot, dot and have many more C-naughts. But let's just say in this example, there's two C-naughts connected to this ancilla. And this, if you just translate every gate and preparation gates and measurement to the ZX calculus, then you get, well, this is the ZX diagram, and you can fuse it, and that's what you get. And you can also view this as computing the parity of the computational basis states. So if you plug into Z basis states, ket 0 or ket 1, or either of them can be ket 0 or ket 1, then this will take the XOR of those two. And so on. So in general, these are doing parity checks. So this already gives us a way to go from between circuits, and by doing these like fusions, then you get XOR and parity operations in the Z and X bases. An operation P on the physical qubits implements a logical operation if this K qubit map L is equal to the encoder map E, then this N qubit physical operation P, and then encoder dagger. This is just by definition. Something that we've been looking at in Grok, well, it wasn't called Grok, but the QPL paper, I think this idea was first put out in the QPL paper by a lot of people. Sarah, Jackie, me, Alex, Mike Mosca, and Mike Vasmir in QPL 2023 proceedings. So we looked at pushing through the encoder, which is a sufficient condition for this top equation here. So long as you do L then E is equal to E then P, then that implies the top equation on this slide. And we call this pushing through the encoder because you could start with the desired logical operation L and just push through E, and then the ZX diagram you get at the end is exactly what P should be. And we showed in that paper how to push arbitrary ZX diagrams through arbitrary phase-free ZX calculus encoders. So works for any CSS code. So, and as for if the implication, what is the necessary condition to add, conditions to, or in this case, one condition to add for the other direction to hold. So this bottom equation implies the top equation whenever the operation P preserves the code space. So as long as it doesn't take you out of the code space, then this is sufficient and necessary. Just to bridge if someone was coming from a more group theoretic presentation of stabilizer codes, then just to match on terminology, then stabilizer codes, this code space is equivalent to a stabilizer group. Let's call it curly S. We will never use curly S again in this talk, but where this is a subgroup of the n qubit polygroup. And conventionally, you take the code space to be the joint plus one eigenspace. So you take all the signs of your measurements to be like plus one instead of minus one. That's a convention, though. You could also just add a sign bit to your Tableau if you didn't want to deal with this convention or didn't want to force this convention. So the centralizer of a subset in a group is the set of elements that commutes with every element of that subset. So where that's relevant is that, let's hear this diagram. S is our code space, so all the stabilizer generators and stabilizers spanned by them lives there. All the logical operators live in the centralizer of S, so this yellow part, and that means that they must commute with everything in S, the pink part, but then they might not necessarily commute with each other. And in fact, they can't commute with each other because like poly X on like the first logical qubit can't commute with poly Z on the first logical qubit because X and Z don't commute, for example. And any detectable errors live in this blue region, which does not commute with the stabilizers, and therefore when you measure, then it will give at least one of the stabilizer generators that you measure is going to give a -1 sign, because at least one of, to be in the blue region, that means you don't commute with at least one thing, in fact, many things in the pink area. Here, this part of the talk, and wrapping up the first part of this talk, is these representations of stabilizer codes. So I've just kind of thrown 6 common ones here. We'll talk mostly about the first 5. But this paper is about how to go between all of these, except maybe not geometry and topology, except in cases where you can overlay them, but for any stabilizer code. So here's like just some quick and dirty definitions or recaps of the as well as what they look like. So a stabilizer tableau for a stabilizer code is a linear map over F2. So you can think binary matrix that is n minus k rows and 2n columns, where again k is the number of logical qubits per code block and n is the number of physical qubits for your code. And sometimes conventionally there'll be one extra column for the sign bit of what is the sign of those polystrings. But conventionally in quantum error correction, you take +1 to be the joint, to be the sign for all the rows. So we'll just deal with that case, even though it's not so much, it's just extra bookkeeping. So for CSS codes, this is the fragment. This corresponds to the phase-free fragment rather than just the stabilizer, rather than all of the stabilizer fragment of the ZX calculus. So for CSS codes, it's special. So that instead of just like more arbitrary binary matrices where all the rows are independent, they specifically factor in this way, such that there exists some way to write the tableau such that it's block diagonal. And so the left half of the tableau is about, if you put a 1, if it's stabilized by poly X, and then the right half of the tableau, every time there's a 1, then it's stabilized by poly Z. And whenever you have a 1 on both sides for the same element, like the same location of your binary matrix here, then it means stabilized by poly Y, because X times Z up to a global face is Y. So for CSS codes, this tableau is of this nice form, and this essentially lets you have many special properties that are really useful, specific to CSS codes that don't nicely generalize well to arbitrary stabilizer codes. We'll show maybe as a recurring example in this part, the Steen code, also called this, identified with the number 713. So 7 physical qubits and 1 logical qubit. and code distance 3. So it can correct and detect up to 1 error per code block. So here for the specific example of the Steen code, then the binary matrices here would be this H sub x and this H sub z matrix shown here. For CSS codes, they're often identically to the Tableau. You could also use a graph to represent them. So let's say you've got the bi-adjacency matrices of these graphs are H sub x transpose here because I've drawn it to the left, and then H sub z. So put a 1, so in the matrix, there's a 1 if there's an edge in this bipartite graph, and there's a 0 if there's no edge between that left node and that right node. And so this is exactly the same, just drawing it as a bipartite graphs instead of as binary matrices. For stabilizer codes, so as we showed before, you can think of it with the projector picture, which is this code space projector onto the code space, which you can further decompose into n minus k projectors for each stabilizer generator. So for CSS codes, in fact, this code space projector picture is actually identical to what it looks like for this tenor graph representation. So this is quite nice, this normal form. For any CSS code, this tenor graph, you can get a phase-free ZX diagram for the code space projector, which is exactly the same shape as the tenor graph. So, so that's quite satisfying that you interpret it as a linear map rather than just storing the information of the checks for the ZNX basis parity checks. So one kind of natural question is, can you generalize tenor graphs to stabilizer codes? Because the correct generalization could be like something that's also a code space projector, for example, which we'll see later in this talk. So syndrome measurement circuits. So this is some common ways that quantum error correcting codes are presented in the literature is that they show this circuit, and these are the measurements you need to do for every round of error correction. So in this example, this is also for the Steen code. Then you measure these 6 stabilizer generators. So earlier we had 6 rows of the Tableau, 3 for Z and 3 for X. And yeah, if you write this in ZX, you'll see that you exactly get the code space projectors seen before. So that's a simple example. Also, if you also specify with this encoder picture how logicals are mapped to physicals, then this left-hand side phase-free ZX diagram for the encoder for the Steen code, the 713 code, is you could also extract a circuit from it. So this is a C0 circuit acting on Kep plus and Kep 0 and Scylla. One for each stabilizer generator. So this is an encoder map. So this is non-unique for any code because there's many different encoders that could work for any code, but all the encoders are equivalent up to a k-qubit logical unitary. So a k-qubit unitary in the logical qubits beforehand. So that's why for many useful properties of the code, you can just pick n encoder. But here in this talk, we'll go through any Clifford encoders for any stabilizer codes. And lastly, this is maybe just to like help connect the dots, but we don't say anything more about it in this talk. So when you have code geometry and topology, it often means there's some kind of geometric or topological description. And it might be like, oh, on the edges or on the nodes or on the shaded regions, there'll be some like X or Z checks or some different like describing how those checks are. So this is really convenient to do with the ZX calculus because you can just like overlay a ZX diagram with that precise connectivity to be those checks. So you could even use the X, Z, and XY or Z calculus, like also use Y if you happen to have like XYZ symmetry kind of situations too. But like say the Steen code is just CSS, so you just need CNX like this. You can just overlay on each region. There's these checks. And in the special case of the Steen code, for the phase-free, like for the diagram, if you like made the input node red instead of green, and like that's also a valid encoder. So we'll talk about phase-free normal forms, I think, next. So now we're at the second part of this talk. This is about normal forms for Clifford isometries. We'll start with the phase-free case and then go on to arbitrary isometries in the stabilizer fragment of the ZX calculus. So this year definition is for generalized parity form, which is a normal form introduced in the Picturing Quantum Software textbook preprint by Alex Kissinger and John van der Wetering. And this is for any phase-free ZX calculus diagram. Here's the definition, but essentially it looks like this. There's the main feature is like there's a bipartite graph and then two more bipartite graphs hanging off the ends of them. And there's two of them. There's the Z-X GPF, which is like Z spiders on the inputs and X spiders on the outputs. And then there's the X-Z GPF, which is X spiders on the inputs and Z spiders on the outputs. So essentially for this talk, we're only interested in the special case of this when J equals 0. This is because if you ever have for all isometries that in the phase-free fragment of the ZX calculus, it must be the case that J equals 0. This is easy to see by seeing that because if J is non-zero, then there must be some post-selection, which means that there must exist some inputs that are annihilated by that map, and therefore it can't be an isometry. So I should comment, this does mean that we are essentially dealing with bipartite graphs for any isometries. So can I scribble? Let me know if you can't see this. But like look at this Z-X GPF on the left. So we're essentially dealing with phase-free diagrams of this shape because we don't have this stuff because J equals 0. So essentially we're able to describe these graphs by knowing the input number of inputs, number of outputs, and knowing this bipartite connectivity, and knowing how many, what is this number here? Okay, I shouldn't be allowed to draw anymore. It's not very good, but no, I can clear it. Okay, there we go. Yeah, so we can look at an example of a phase-free ZX calculus encoder in this normal form. For the 422 code, which is like the smallest, like maybe non-trivial CSS code. So looking at the code space projector of the 422 code, there's only 2 rows of the tableau. It's just one way for X measurement. X-type stabilizer generator is a Z spider. So that thing is a Z spider, but it's called an X measurement because Z spiders is stabilized by doing poly X on all the legs. So like X here and on the other 4 legs, because you could think of it, it's just because it's a GHZ state. And there's also a weight for Z type stabilizer generator. So that's it for the tenograph for code space projector of the 422 code. An encoder for this code means that there's some selection of which poly Z and X on the logicals maps to which physical operations. Because we want to choose the N encoder, which is phase-free, which you can always do, then okay, I'll show on the next animation. But essentially, you can choose the choice of poly Z and X logically, and what physically implements that. You have both Z-X and X-Z GPF for any phase-free diagram. So having the encoder diagram be a phase-free diagram, you have this constraint that the Z-X and X-Z GPFs must be equal to each other. So it must be the same linear map. And equivalently, there must be, if you apply the GPF algorithm to both of them, they're the same linear map. Given this encoder, some phase-free encoder in both Z-X and X-GPF, such that those are equal together, this pair of diagrams in GPF is enough to let you read off the complete stabilizer tableau for any CSS code. So in this example, I just show how to read off logical x1, but this works for all rows of the tableau. So here on the bottom left, you started with logical x on the logical first qubit. Then you push that through the encoder, in this case, just copy, fuse, unfuse. And then finally, at the rightmost bottom diagram, then you get physical x on the first two physical qubits and then identity on the bottom two physical qubits. So this, in essence, this is a proof that x1 bar, so logical x on the first logical qubit, is equal to xxii on the physical qubits. You can do the same to read off logical x2 bar, and then from here you can also, with this third diagram, with this third node subdiagram here, this is the wave 4 x-type stabilizer generator. You could start by pushing through the encoder, but it doesn't actually push through. So you have if you were to have 4 physical x, so poly x's here, then that would fuse with this, and then you could unfuse with them to be here. But then a GHZ state followed by 4 x's, one on each leg, is just equal to just the same GHZ state, because that stabilizes it. So that therefore shows that XXXX is a stabilizer here. Now you can repeat the same reasoning with the other normal form, but now for poly z's. So this normal form instead, that's equal to this one here. And that lets you read off logical z1, logical z2, and the stabilizer zzz. And this process generalizes to any CSS codes given any phase-free encoder of it, which always exists. So we now want to look at arbitrary stabilizer codes and normal forms for them. So we can look at existing normal forms for stabilizer states in the ZX calculus. So this can also be applied to diagrams which are not states. It's just that effectively you're applying those rewrites to the Choi state of those diagrams by just spending all the inputs into outputs. Equivalently, you could think that it doesn't really, the algorithm for these normal forms doesn't distinguish between inputs and outputs. So let's start with some generic ZX diagram in the stabilizer fragment of the calculus. This essentially means that all your phases in the whole diagram are integer multiples of pi over 2. And Hadamards are allowed, of course. Then just doing spider fusion and color change is sufficient to get to a graph-like diagram. So these are things with like Z spiders and then Hadamard edges between them, roughly speaking. Then you can do pivoting and local complementation to get to something that looks like this. This is just a choice of representative, like what it looks like diagram. And from here, you can split off into 2 different directions for 2 different, like most common classes, the 2 main classes of normal forms for stabilizer diagrams in the ZX calculus. So one of them is the graph states with local Cliffords form. So this means that you have a graph state. So this is Z spiders with faces on them that are connected by Hadamard edges between any 2 of them. And you can have local Cliffords. So single qubit Cliffords on any inputs or outputs. It's not really distinguishing between them. So you can think of it as just on any of the wires, open-ended wires. So one way to think about this pivoting operation is that it's similar to Gaussian elimination that you would do if you wrote these diagrams in a Tableau form. We can say more about the Tableau equivalent of GSLC form in a bit. In the other direction, you can have affine with faces normal form, and this means that all your internal spiders are red, or X spiders. All your out boundary spiders are green, or Z, and then they're connected by a bipartite graph of non-Hadamard edges. In addition, you can have Hadamard edges between the outputs. So we'll see more of that too, and talk about the Tableau consequences or correspondence of that. We will also briefly discuss, but we don't need to use it in this talk much, except it simplifies the reasoning a bit, is reduced AP form. So this just means that you've done some additional Gaussian elimination such that a subset of your boundary nodes have no phase on them and no CZ edges. And that it's called Gaussian elimination because it's equivalent to having done Gaussian elimination on the Tableau. So if we apply GSLC normal form to any isometry, what we get is going to be always of this form. It's going to be single qubit Cliffords. If you further reduce, say, with like pivoting and local compensation, you can actually make these local Cliffords in terms of just like Z phases and Hadamards. So get rid of any red like pi over 2s or pi's, for example. Yeah. Let's just say local Cliffords. And there's going to be a bipartite graph between the input and output Z spiders here, these two layers. And there's also going to be CZ edges. This A prime and A adjacency matrices determines those CZ circuits on the K input qubits and the K output qubits. So one thing to note is that in quantum error correction, people usually don't care at all about the single qubit Cliffords because they usually ignore them because they don't change properties of most properties. In fact, almost all properties that are interesting for the code. So these single qubit Cliffords don't change the code distance. And it's just like another almost equivalent code. So it is well known that any quantum error correcting code that is a stabilizer code is always equivalent up to local Cliffords to some graph code. So graph codes would be this inner part here. This encoder would be an encoder and a description of the graph code. And so any stabilizer code, you can have a Clifford encoder for it, and then all Clifford isometries are always up to local Cliffords on the inputs and outputs equal to some graph code. So one kind of first question here is that the question we were interested in is, could you read off, and if so, how much or how would you do it to read off a Tableau from stabilizer codes, as opposed to it kind of follows from the ZX diagrams that we had for CSS codes. So we can first ignore this k-qubit input logical unitary on the k logical qubits. We can just ignore that. The reason is because all encoders for the same code are equivalent up to a k-qubit unitary on the logical qubits. So if we just want to read off a stabilizer Tableau for the code, it just needs to work on, it will be the same for all possible encoders. So we just pick whatever's easiest. So let's ignore that and ignore the input local Cliffords and the CZ edges. So this is what we're left with. And this lets you directly read off a stabilizer Tableau for the choice state of the encoder. So, well, technically this lets us read off just from this part. And then whatever you read off for those polystrings at the end, just this is a really easy like rewrites to do of like changing your polystrings. You just change like all letters in that column by whatever operation, whatever is the equivalent symplectic operation that's specified by the single qubit Clifford gates. So we'll just focus on reading this because then commuting it past this layer at the end is really easy. So specifically, all you have to do is to read off a stabilizer Tableau for the choice state of this encoder is for each open wire, this total n plus k, put a poly x on one of the open boundaries, so whether it's input or output. So let's just say put it here, for example. And then that poly x will also copy to all of its neighbors in this B, and if it's on an output, maybe it also has neighbors with this adjacency matrix A as well. So its neighbors in this the graph state corresponding to this encoder. And so you can stabilize that by doing Z on all neighbors. So we'll do an example next. So here's an example with the 513 code, also a really nice small and non-CSS stabilizer code. So this is in GSLC, so there's a local Hadamard on the input, but that's fine. So you could put after the local Clifford, so putting a poly X here, this is pushing it out, putting two poly X's here, basically. You can push one of them left to get this poly Z through the Hadamard and one of them through this, and then it becomes these 5 poly Z's, and I can't circle, so that's what you get. Yeah. Doing the same on the right-hand side, what you get is, let's see, yeah, let's say you put let's say you put poly X on the second output physical qubit, then that means putting poly Z on all its neighbors. So it's connected by a CZ edge to 1 to the input, and that poly Z through this local Clifford Hadamard becomes poly X, and then 2, 3. So therefore, doing logical X on the logical qubit is equal to doing Z, X, Z, I on the physical qubits. So this lets us read off a stabilizer tableau with 6 independent rows, and this is what we want for being able to recover, and this completely describes the encoder map. However, this doesn't tell us directly about the stabilizer tableau of the code, because we actually have 6 rows of the tableau, which is the correct one we need, which is n plus k, for it to fix the encoder. But we are missing, all 6 of these are logical operators. And so we would have to do additional row operations and additional computation if we wanted to read off the stabilizer tableau for a stabilizer tableau for the code. So actually knowing what the code is. And that's that's quite interesting because it made it seem as if you can have more specific rewrites or subversions of the graph states with local Cliffords form, but it's not very helpful for reading off properties of the code. We looked at the other main of the 2 classes of ZX calculus normal forms for the stabilizer fragment, called affine with phases form. So this form, I guess, is lesser used in the quantum error correction literature because the former of the forms is well known with like graph codes. So this form is for stabilizer states in the ZX calculus. For ZX calculus, it was independently discovered by both Backens and McElveny and by Kissinger and van der Wettering. And it's based on the normal form representation for states, but like with bracket notations by Dehaene and De Moor before that. So we'll first show how to read off a tableau for stabilizer states with affine with phases local form. Sorry, affine with phases normal form, called AP form. So AP form is specified by 3 parameters. It is a biadjacency matrix B. It is a binary vector little b here. And it is a adjacency matrix A, although technically this is like a adjacency matrix that also allows like elements on the diagonal. So you could also think of this, I think in previous presentations of this, they also used a function which has a linear component and a quadratic component. So the linear component is like it acts on only just one of the computational basis state in the total superposition in the sum. And then the quadratic component acts on based off, it's a CZ edge. So it's triggered when you have like x times y for x and y bits corresponding to the two qubits that are touched by that CZ. So for example, here's just some artificially looking diagram for an example. So here, little b is 101. Big B, the biadjacency matrix is like the first one is, yeah. This one is connected to 0, 1, 0 because it's not connected to this one. It's only connected to the middle one. This one is connected to 1, 0, 0, yeah. And then 0, 1, 1, and so on. And then this adjacency matrix A is like, let's look at the diagonal parts first. So this is e to the I pi, e to the 3 pi I over 2. So this is 3. This is base rate 0. And then this one is e to the 2 pi I over 2. So that's just pi. So that's why it's 2. So that's the integer multiple pi over 2. And then for the CZ edges, there's a 1 if there's a CZ there between those two. So the CZ part, the off-diagonal part, is symmetric because it's an adjacency matrix. So there's a 1 here because there's a CZ edge between the first and third qubits. So like that here. So this we'll start we're looking for the isometry equivalent of this to help us read off the normal form. Although we did a bunch of mucking around first, but so we're looking for a decomposition of this form. We actually have strong reason to believe and that this is a good form to look at. To look for because there was an observation in a recent years paper by Webster, Quintoval, and Bartlett in the New Journal of Physics that said that any stabilizer code is decomposable into 3 layers. So a CSS code, polyexis, and then finally a diagonal Clifford unitary. So this observation isn't new for codes, but they hadn't looked at isometries. Moreover, this paper just stated the observation but didn't do a thorough proof, and their construction wasn't efficient. So their construction to find the inner CSS code given a stabilizer codes it was just like linking to a GitHub repo, which kind of brute forced, so an exponential algorithm. So the question is if there's a efficient algorithm, and in addition, does this actually relate to tableaus in any way? And if this gives us a normal form for isometries. So all these questions kind of boils down to this U mystery, and if there's an efficient algorithm to take any isometry of diagram of the encoder to get it to this normal form. Where this U mystery is some unitary that we're going to find. We also, kind of before learning about this observation by Webster, Quintoval, and Bartlett, we also were looking at this form because it, I guess, not only seemed to come from, was familiar to look at from the state AP normal form. Also, a few examples, we could find examples of CSS codes followed by CZ gates. And also, oops. We know that for CSS code encoders, we have this XRC GPF, so that's how we chose something that looks like this. And then all encoders are equal up to k qubit unitary, so that's why we tacked on this. But this is just observation of the kind of form we're looking for. But how to get here is another question. So this slide is gonna go around and effectively describe the sub-steps to get there. So starting with an arbitrary Clifford isometry, So all Clifford encoders of any stabilizer codes will be some Clifford isometry. Um, we can do the usual AP normal form algorithm on the Choi state, so bending all inputs into outputs of the encoder map. And that's our starting point. So next, although this part of the process isn't necessary, it does make the algorithm a bit simpler to do. So why not? And all these arrows are efficient. So you can do reduced affine with phases form. So this is just Gaussian elimination. So this just tells you that you have pivots. So going through what it looks like for reduced affine with phases normal form. This is defined by, I've sort of rewritten this definition just to align better with the variable names we used in this talk, but they should get the form. So it's this triple here. And the big difference, the main difference and the only difference is that the biadjacency is now in reduced row echelon form. And then the phase function that applies phases based off the computational basis states that are in the sum of the affine part first. That's only applies to free variables, so not pivots of this reduced row echelon form. So essentially, this means that you'll have some of these outputs of this AP form over here on the right-hand side. Some of them will just be like a green spider on its own with no face and no CZ edges. So all of those will be pivots, and you'll have a number of them. It's a bit hard to draw without loss of generality because it's not necessarily the case in the general case that like let's say all the pivots are at the top. Like if that's possible, reduced row echelon form would make that happen, but that's not necessarily the case, so that's why I didn't draw it. But you can imagine that. So a theorem is that reduced affine with basis form, or RAP normal form, is actually a unique normal form for any stabilizer states. And that just follows from this theorem that this affine with faces like representation of any stabilizer state is unique once you've done the reduction so that this is a free variable. This is only applied to free variables. Once you've like RREF'd those other ones, the B's. Where this phi is just the phase function that does the linear part for the diagonal parts of A and then does the quadratic part for the off-diagonal parts. So that's where we're at so far. And now to the main part of the, I guess, this work, which is to unchoy the state AP normal form back to isometry and then by OCM, and then the algorithm to get to isometry AP normal form after that. So unchoying just means bending the wires. So this is a K plus N qubit stabilizer state, which is the Choi of our Clifford encoder. To unchoy, we have to bend the wires back. But we want it to be, well, not a mess. So let's unfuse parts of this phase function A. And then you can transpose the K inputs, which is the unchoy part, and that's what you get. So you get a diagonal Clifford on the inputs. You get a diagonal Clifford on the outputs. And you get this nightmare thing in the middle. Not nightmare, but it's a lot of stuff. And so basically because we've already unfused these things, we can just like ignore them and focus our attention to, because those are unitaries, then we're trying to get an isometry normal form. We can ignore the unitaries and just focus on getting a nice normal form for this. Not just because of the unitary, sorry, it's because they fit the description of the thing that we were looking for, which is some unitary on the front and some diagonal Clifford unitary at the end, and then some isometry in the middle. So in the end of the day, this is our normal form. So what is the U mystery on the inputs that we had before? It is this. This is a 3-layer circuit decomposition. The 3 layers is some diagonal Clifford unitary, some layer, there could be Hadamards or not Hadamards on each of the qubits. And then there could be, I didn't know how to name this, XX gates. I don't know, because they're the X version of CZ gates, but you can't call them CX because that's already taken. So I just called them XX gates. I don't know. We just decided on that so that they look like that. And so those are the three layers. These layers are not independent, but like they look quite minimal. I don't think you can get less than that. Um, so we basically, after our normal forms rewrite, what we ended up with is always of this form, where U output is a diagonal Clifford unitary, and U input is always going to be in these three like layers with a CSS code in the middle, although you can have poly X's here because you can have because it depends on if your convention for the joint +1 eigenspace or not. But for arbitrary Clifford isometries, yeah, you can have pi phases here. This is the algorithm. This is the steps of the algorithm. Presenting in a tree, like a flowchart form, makes it clear that we cover all the cases. Although I won't go through all the detail of the proof because it's quite technical and probably not the best use of time, but I'll kind of show pictures of what goes on in the different cases. So essentially, for every input of the isometry, we just ask, is it already a pivot? If so, then you don't have to do anything. The reason, because if it's already a pivot, then it has no CZ edges. It has no face. And we want to get rid of all the CZ edges. We want to just delete all CZ edges on all the inputs, basically. And we wanted to delete all non-CZ edges to these red spiders. So that's why we want to make all the inputs pivots. And if it's a pivot already, you don't have to do anything. Then, yeah. Not to all the red spiders, sorry, my bad. It can be connected to exactly one red spider for the inputs. Because it has to be for the isometry, but you don't want it to be connected to more than one. Sorry, my bad. No. It can be sorry, it can be connected to more than one red spider. It just cannot be connected. Yeah. Okay. Sorry. It is going to change from a green spider to a red spider, and the red spider can be connected to these green spiders. Yeah. Yeah, this picture. Sorry. So we want to make these green spiders pivots such that you end up with a red spider that can be connected to any of these green spiders. Yeah. So if it's already a pivot, you don't have to do anything because the one green spider is just identity. If you have many X spiders connected to it, depends on how many. If you have 0, then you can change that green spider into a red spider by doing this. If you have more than one, then you can get it to always be equal just to 1 by just adding that red spider to all of the other ones connected to it. So here, this example, you wanted this one to be connected to just one red spider, but it's actually connected to 2. Then you just add one of the red spiders to the other. And then adding them, because this is just addition modulo 2. So then in the end, this one is happily connected to just one red spider. Then if you're here, that means that only one red spider is connected to that green spider. If it's not if that thing already has a pivot because of the reduced row echelon form, if that pivot was an input spider, another input spider, sorry, if that pivot was an output spider, then you can change that pivot from being the output spider to an input spider. So just change the pivot. If that pivot was another input spider, then you have to do something a bit more complicated, which is essentially you can like unfuse this XX gate with a Hadamard here. But yeah, I wouldn't yeah. Yeah. and then that creates a new red spider internally. And so and this gets shoved into the input unitary, and then this new red spider is happily such that this is its pivot, and it's not connected to any other red spiders anymore. So yeah, that's the main part of the talk, the main result. And the rest of this is like kind of a smorgasbord of different connections we can do between different representations, thanks to have the knowledge of the normal form. I do know time-wise, I kind of made more slides than necessary, knowing that we probably wouldn't be the best use of time to do too much of part 3. But feel free to stop me at any point for questions or for if you want to wrap things up. But otherwise, I'll keep going.
But Leah, I think we can ask audience if they have any questions now before we move
Yeah,
on.
good time.
Yeah, Cole, please go ahead.
Can you hear me?
Yeah.
Yeah, first I have a comment and then a question. So the comment is that the generalized parity form, I think was first discovered by like Filippo Banchi and his co-authors, and they called it like the span form in a more general setting. And then the second question is that Cleve and Gottesman have this paper where they give a unique normal form for stabilizer codes. And when this is restricted to being full rank, so that it's a stabilizer tableau, then the data of the normal form is in bijection with the data of the reduced AP normal form. So I'm wondering, in the general setting of the normal form for a stabilizer code, is there some connection with your normal form for Clifford isometries? Because of course the stabilizer code is up to precomposition with a Clifford unitary Clifford isometry.
I have looked at the Cleve and Gottesman paper, and I could tell it was a different normal form, but I haven't made the connection between the normal forms. So I don't have a thorough answer at the moment, but I know that it's a different normal form.
Okay, yeah, for me it's just kind of confusing because there's so many like matrices and so on. But I know that at least for stabilizer tableaus, then it's the same as the stabilizer as the reduced AP form. I mean, it's the same data, so it's like seems very similar. If it's not the same, I don't know. But thanks.
Yeah, I'll get back to you on that one. At least I think they didn't mention a circuit decomposition that looks like this one, or because it's also in a different language, it's described differently. They use
Yeah, the only
this.
this the stabilizer codes like the tableau kind of thing, not the no circuits, just the matrix.
Yeah, so that in particular that opens a one question is that in the next part I'll talk about the tableau normal form that corresponds to this this isometry AP normal form, but we actually don't know what is the equivalent tableau operations to do these. We know we can just always, given any tableau, we can get to the tableau normal form by doing ZX operations and getting to isometry AP normal form, but we actually don't know what is the operations you do on the tableau, like to get the normal form. So we don't have a like Tableau only algorithm that is, but we know there must be one that exists for that. That is the Tableau equivalent of our ZX algorithm. So that's something we really want to know, but it's very confusing.
Thank you.
So maybe Leah, in light of time, maybe we should move on and then save the remaining questions to the end of your talk.
Okay.
Make sure you don't ask.
I just
Yeah, go ahead.
maybe you were going to get to this. So part of the promise that you made in the beginning was that this normal form is very particularly good for seeing that connection between the tableau and the normal form. Could you help me how to exactly read off the stabilizers, because I don't fully see
Yeah,
that.
that's this part. That's algorithm F, and I'll have an example. I just thought that probably goes in the third part of the talk instead of the second. So we should go onwards. So now we'll talk about algorithm F, because we named them A, B, C, D, E, F for some reason. That is to go from this isometry AP normal form to a complete stabilizer tableau for the code, and fixing the encoder map. So now we've essentially completed this bijective arrow, because we can go from right to left as with all these efficient algorithms from A to F. And then we can also go from left to right because you can just you can just write down, the complete stabilizer tableau as a series of like poly measurements on the choice state. So like you would usually like say like those projectors that we showed earlier, just do that and then unchoy, and then that gives you E. So this algorithm F proceeds quite similarly to the CSS case, which is quite satisfying. You read off the stabilizer generators that are such that those poly strings where the letters are just from Z and I. So you can look at these ones. These internal X spiders. Each of them is connected by this bipartite graph B to these output Z spiders. Let's say like this one was connected like here, like to these first one and last one. Then this is stabilized by poly Z's on all connections. And those poly Z's like will fuse and unfuse, so they commute with all Z spiders. So in other words, these purely Z-type stabilizer generators, these stabilizer generators that are only made of Z and I, they always commute and with this diagonal Clifford unitary. And so they're the same for the inner CSS code and for the stabilizer code. So this is like the easy case where you don't have to do anything but just read off what like you usually would from the CSS code. So you can, as a side note, actually, before we go, this reduced AP normal form, this inside this orange here, you can view that as being connected to this green. So in essence, this is kind of like one way to generalize Tanner graphs from CSS codes to stabilizer codes. This is like one of the two projectors. You could have it like this, for example. But you'll need another projector because this is just, well, this is just the poly strings, the stabilizer generators that happen to be over Zi. And then, of course, you can have things over X and Y mixed in as well. So you might not have any stabilizer generators that are over Zi, in which case you would have zero internal, then you would have zero internal red spiders here. So now you can unfuse the diagonal Clifford unitary to read off the other stabilizer generators. You output, so unfuse this part, and now change the inner CSS code encoder, which is a phase-free ZX diagram. So change it from being x-z GPF to z-x GPF. It's not really an issue that you have these red pies over here because all of the GPF algorithm rewrite rules still work if you have the pies. You could also equivalently like unfuse the pies and then like fuse them back in. So that's fine. And then when you have z-x GPF, this lets you read off the X logicals and the X type stabilizer generators of your CSS code. CSS code complete stabilizer tableau. So, and then all you have to do, read off this stabilizer generators over xi, x and I from z-x GPF, and then you have to push these through u0, uo, which is u output. So the u output is this diagonal Clifford unitary. So if you have a red x, if you have an x here, then it will copy across the green. Possibly because there might you might gain a green pie, possibly, depending on if this was an escape. S or S aggregate. And then you'll get a red here on the output, and then you also get Z's on all the neighbors in this CZ circuit adjacency matrix. So you can, so you'll just have to push through. This is equivalent to doing a binary matrix multiplication, as I'll see on the next slide, I think. So likewise, you can read off logical operators from the input spider connectivities, and then you have to push them through UI if you've got that, which is just some diagonal, which sorry, not necessarily diagonal. It's some Clifford unitary if you have a Clifford encoder. So an example would be much better. So here is the 513 code as an example. So here's a graph-like diagram. Actually, it is GSLC form already. But we don't have to go to GSLC form, but just graph-like diagram. The inner CSS code for the 513 code encoder is this. So it's a bit trivial, but it's just a red spider with connected to 5 physical qubit, but these are just identities. There's just like one input, one output, but this is the x-z GPF. And from this, we can read off for the inner CSS code, z bar is equal to z. And then that will just can commute through this diagonal Clifford unitary. So that's also z bar for the outer stabilizer code, the 513 code. We can then do the same for changing this inner CSS code's x-z GPF to z-x GPF. And this gives us, this lets us read off x bar is equal to iix, because just numbering from 1, 2, 3, 4, 5, then this one is only connected to the 5th one. So iix. But that's just for the inner CSS code, and we actually have to push that through. So when we push that through, we get x x here pushed through here becomes zx, and so that's why logical x for the whole 513 code is xiizx. And we can do the same with the stabilizers. So for the inner CSS code, because we don't have any pure Z-type stabilizer generators, there's no internal red spiders, so we didn't have to do anything. Here we have, let me draw, 1, 2, 3, 4, like that, 4 internal Z spiders that are of the inner CSS code. And so these they're each independent here, and these are each a X-type stabilizer generator because they're Z spiders. So this one stabilizes, for this one, we can read off for the inner CSS code XXIII because XXIII, because it's only connected to the first two. And then we can push these two poly X's through this CC circuit, this pentagon, and that will copy into X here, and then Z on all the neighbors. So Z, 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 but Z times X is just Y. So what we get in the order is like Y, Y, Z, I, Z, which is this one. And in this case, it's cyclically symmetric, so you can just, the other 3 cases are the same. But you actually only need 4 rows. You don't need the 5th one, because then they wouldn't be linearly independent if you also include like the logicals. So and we know the total number of rows of your complete stabilizer tableau should be 6 in this case, because it's n plus k, so 5 plus 1, which is 6, and these are independent. So these poly operators that we could read off up to this pushing, but we can read off what to push through. So we could read off these 6 poly operators forming these 6 independent rows of the complete stabilizer tableau. So it's both the tableau for the encoder map, as well as a subset of those rows are the stabilizer tableau for the code. And we essentially only need to have 3 pieces of information to specify to read off from. So we need two ZX diagrams, but they are equal to each other. One is this bi-adjacency connectivity here. The other is this bi-adjacency connectivity here. And the third is this, it's the same one on both diagrams. It's this diagonal Clifford here. This is adjacency matrix for the CZ circuit and possibly with S gates. So we can prove that, well, I mean, I guess the proof is just by reading off that this works for arbitrary Clifford encoders of arbitrary stabilizer codes, that we can always read off a complete stabilizer tableau. The number that we have is correct. It's neither too few or too much, and they're all independent, and for both the tableau and for the encoder. And in particular, this means that we have essentially a normal form for the stabilizer tableau of the code in this form. So this is it looks, if you recall, it looks exactly like the CSS code case of the tableau, except instead of a 0 in the top right quadrant, well, they're not equal size, but like these n columns up here, instead of a 0 here, you actually have mx times g, where mx is the x parity checks matrix, and then g is this symmetric matrix, which is precisely like the determined by the A part of the AP normal form, the adjacency part. And it's a symmetric matrix because it is, well, symmetric means self-transpose. And we've been trying to ask around if people have seen a Tableau normal forms of this form for arbitrary codes, and haven't found anything yet. So if anyone knows, please let us know. And quite interesting is that even though we just have an algorithm to take an encoder, a Clifford encoder, and get from that a Tableau for the code in this form, in this normal form, we actually can also use that information to write arbitrary stabilizer tableaus for arbitrary stabilizer codes into this normal form, even if we're not explicitly given an encoder. So we can still basically find mx, g, and mz given this information. And in fact, the existence of this normal form actually does help a lot in doing this derivation, because we can take this knowing that any encoder must follow this decomposition, and that helps us with the reasoning to do this. But I won't show it today. Here's just some like bonus materials, but for connecting the more dots between the representations. So for any CSS code encoder in phase-free Z-X or X-C GPF, we can always extract a CNOT circuit. So for the inner CSS code, or just for CSS code on its own, essentially the key step is a Gaussian elimination. So Gaussman has, of course, Gaussman's done everything, but like Gaussman did this in his thesis, I think, I don't know, probably his thesis. But you can do some kind of Gaussian elimination to like extract CNOTs from the pivots for CSS codes, and you can do a similar process for stabilizer codes.
We have to go, but thanks for your talk. Yeah.
Thank you, everyone.
See you.
And as a corollary, you can extract any Clifford encoder circuits of any stabilizer codes, any isometry because you can have the CNOT gates for the inner CSS codes, and then you have CZ gates as the entangling gates for the diagonal Clifford unitary that comes after. You can also do encoder circuit extraction. So extract an encoder, well, it doesn't have to be circuit, just in normal forms, but sure. Because of the previous from the normal form get to the circuit algorithm for any stabilizer tableau of the code. So if you're not given, in other words, if you're not given a choice of logicals, you can still pick a choice of logicals that necessarily commutes with all of the stabilizer group graphically. So it suffices just to extract for the inner CSS code, because once you know MZ, MX, and G, you can just tack the diagonal unitaries on the ends afterwards. So for each stabilizer generator, you commute it to the middle and split. So you're starting essentially with a bunch of stabilizer generator projectors, one for each stabilizer generator in series. And let's just call one part the middle, and the middle is going to be wherever we do the split. And you're going to keep commuting stuff to the middle. So let's just say the first one, let's just say it's X type without loss of generality, because it's all the rules, phase rules are color symmetric. Then you can buy algebra and unfuse, and this lets you have a symmetric diagram on both sides. And then you do the same for all the other generators, and you just commute them through to the middle. When you do the algebra, you do it with respect to the pivot. So you split on the pivot. Then the other generators of the same color, they will just commute through because they don't touch that pivot by definition. And of the opposite color, they will just commute through because by definition, all stabilizer generators must commute with each other. And so that means that the number of edges should be an even number between different types, so X or Z type stabilizer generators, and they'll commute to the middle. And then you can split again on their pivot, and you just keep going. So yeah, and then in the end, you get two phase-free ZX diagrams that are respectively the horizontal reflection of each other, also known as the adjoint of each other, and that is your encoder, dagger, and encoder. One thing to note is that because all other choices of encoders for this CSS code will be the same if up to unitaries on the inputs. So you could change it by unitary here, and then because it's encoder dagger, that would be changed by unitary dagger here. So the unitary dagger and unitary will cancel out. Also, you can add a Clifford unitary here, and then add the dagger of that Clifford diagonal unitary here, and then that gives you for any stabilizer code. You could throw in some poly X's there too. So yeah, after extracting the CNOT circuit, oh, I should have said this earlier. In addition to these two, these two normal forms that if you write them in scalable ZX calculus, they have this form where these biadjacencies are precisely just condensed into these matrix arrows. So instead of one thin wire that's for one qubit, you can wrap like a lot of thick wires. A thick wire represents like this is one or more qubits. Or 0 or more qubits, I guess, in this case. But then the biadjacency matrix is precisely described by these two matrix arrows. It's just that's just a more compact notation, but it also gives really powerful rules of the scalable ZX calculus. So this is the scalable normal form corresponding to Z-X GPF. This is the scalable normal form corresponding to X-Z GPF. And this is the one that corresponds to a CNOT circuit that's that you can describe as the invertible map. CNOT circuits, they're maps as invertible maps in F2. So binary matrices again that are invertible, acting on Kep plus 0 or more Kep plus and Kep 0 and so on. So this particularly lets us have really convenient proofs of certain properties of CSS codes, specifically transversal CNOT. I'll just show it for the k equals 1 case, but you could do some teleportation protocol between code blocks to get arbitrary k greater than 1. But this actually just follows in a really nice way from the scalable rewrite rules for matrix arrows and Z and X spiders. So you can copy matrix arrows that are invertible through green spiders, and you can match matrix arrows of the same matrix for X spiders. So on two code blocks, so this is encoder of the top code block, and this is encoder of the bottom code block, and this is the scalable matrix notation for CNOT, such that the ith qubit on the top block is the control for the ith qubit of the bottom block as a target. So think of like as a ladder where like um like each C naught acts on so each qubit is either the control or the target of some C naught. The main results that we had is a generalized AP normal form from that generalizes the one for states in the stabilizer fragment of the ZX calculus to arbitrary isometries. This helps us go between stabilizer tableaus, graph representations like Tanner graphs and graph codes, code space projector picture, syndrome measurement circuits, and encoder maps. And for future work, we want to think about most direct applications of this could be for searching codes, because then you only have to search codes in this more reduced and therefore cut down your search space a lot, like different variations of these normal forms, different parameters of these normal forms, rather than say like arbitrary binary matrices, which is like a lot bigger space. You can also look at other places where Clifford isometries are used. That doesn't necessarily have to be quantum error correction. So for example, we were thinking about this for fermion to qubit mappings, especially because local encodings are also use isometry, are also isometries, where the stabilizers help shorten the length of the fermionic operators that are encoded into qubits. So yeah, that finishes the talk. Thank you all.
Thank you, Leah. It's fabulous. So feel free to claps or raise the emoji. And if you have any questions right now, maybe it's a good time to ask. So Leah, I have a quick question. So if you scroll back, where you have the extraction of the circuit, yes. So for the leftmost diagram at the bottom, should there be a output wire from the X spider? Because I understand this as you are thinking about the product of all projections to your stabilizer space. So right before the bialgebra, is this intentional of not having a output wire here?
By output wire, you mean of a measurement? Or like here? Like
No, like the one above.
above? Oh, this one. Okay. You mean there's nothing here?
Yeah.
Oh, that's because I was assuming that this diagram is this diagram. So the reason why there's no output wire is because after doing the bialgebra, this has basically cut the wire. So essentially, one way to think about it is that because you started with a n qubit to n qubit map, but you want to factor it into k intermediate qubits here. So you have to like cut things. You have to like you have to compress those n qubits into the same k qubit wires in the middle. So this reduces the total number of wires. Let's say for the very first stabilizer generator that we do this algebra on the pivot to, this reduces the number of wires from n to n minus 1. And we keep doing this for each of the n minus k generators until you get to k in the middle.
Great, thank you. Okay, so maybe we have a last call for questions. Does anyone wants to check with Leah on anything or comment on anything?
Oh, can I make a comment regarding your question?
Yeah, please go ahead.
If you see this in like the density matrix picture, then this is like a way to kind of compute the sign spring dilation. If like you see E and E dagger are like the doubles, and the thing in the middle is the thing that's the mixed state. If that helps.
Yeah, that would work. For any stabilizer, any partial trace of any stabilizer operator.